Okay, we're going to pick up with Chapter 8. So Chapter 8 was all about gases, liquids, and solids, and understanding the behavior of these things, these phases of matter from kind of a macro scale. So the first thing we need that's important from that is understanding the arrangement of molecules and the amount of kinetic energy associated with each state. So if you remember, I would draw pictures on the board back in the days where we used to meet face to face of solids, liquids, I'll abbreviate, gases. We know solids are ordered and arranged. Their molecules are touching, okay? So we said because of that, they have a high amount of intermolecular forces, IMF, intermolecular forces, but they have a low amount of kinetic energy. All right, low amount of kinetic energy, highest amount of intermolecular forces. Liquids, their particles can move about a bit to a certain degree, okay? And so we have more space between the molecules. So they have some intermolecular forces, and they have some kinetic energy. More intermolecular forces and more kinetic energy. Less intermolecular forces, than solids. More kinetic energy than solids. Gases, though, their particles are way spread out, and they're zooming around really fast past one another, okay? And so because of that, we said they have the lowest amount of intermolecular forces and the highest amount of kinetic energy, okay? So that's what I mean when I say understand the arrangement of the molecules and the amount of kinetic energy. Additionally, understand how arrangement energy changes when matter undergoes transitions, okay? So the example of transition changes are things like melting, condensation, sublimation. If you have things that are more solid down here, liquid, gas phase up here. So as you go from solid to liquid, liquid to gas, you are increasing in the amount of kinetic energy. Whoops. I cannot write what I want to write right now. Ke. All right. And you are decreasing in the amount of intermolecular forces at play between the molecules. Okay, as you go down, as you say, so things like melting, okay, things like evaporation. But as you go down from a gas to a liquid or a liquid to a solid, so condensation, freezing, you increase the amount of intermolecular forces between your molecules and you decrease the amount of kinetic energy between the molecules, okay? All right, that's all I wanted to talk about, just understanding phases. The most important thing, perhaps, from Chapter 8 that we talked about was intermolecular forces. A good practice problem for that is 8.35. The three kinds of intermolecular forces are London dispersion forces, also known as van der Waals forces. These are present in all molecules, but they are dominant, meaning they are the strongest force in nonpolar molecules. Okay, dipole forces, they are present in polar molecules. And they're dominant in polar molecules that cannot hydrogen bond, okay? Hydrogen bonding had two requirements. So you had to have a lone pair on an oxygen, nitrogen, or fluorine present in the molecule, and then you have to have a positively polarized hydrogen. And And if those two requirements are met, then that molecule will be able to hydrogen bond with itself. Okay. If it just has one of these two things, then perhaps it could hydrogen bond with another molecule such as water. Okay. The lone pair is what we call the acceptor. And the positively polarized hydrogen is called the donor on the molecules. Okay, a molecule that can hydrogen bond. Also understand how these forces influence melting and boiling points. So London dispersion molecules will have the lowest melting points and the lowest boiling points. Molecules that can hydrogen bond will have the highest melting and boiling points. Okay, so understanding that, if you were given an assortment of molecules, you could then order them by increasing or decreasing melting points or boiling points. Okay. What else from chapter 8? Behavior of gases. So we really then dug into gases, and we talked about we can measure things about gases with units of pressure, volume, and temperature. Okay, these properties allow us to learn about the behavior of gases. So there were several different units of pressure that we introduced, and you need to know, here's the ones you need to know for the final. You need to know that 1 atm equals 14.7 psi, which equals 101,325 pascals. Okay, so know those three units. And then Dalton's law of partial pressures. Okay, so this was Dalton's law. Said if you have a mixture of gases, it was for a mixture of gases, then each individual gas exerts its own pressure. So we had a mixture of gases. So we had an equation for that. We said the total pressure, P total, equals the pressure of gas number 1 plus the partial pressure of gas number 2 plus the partial pressure of gas number 3, so on and so forth, for however many gases you have. If you only have 2 gases in the mixture, then you would not have a partial pressure for gas 3. But anyways, the key thing here for Dalton's law is that you have the same units on all your numbers before you add them up, okay? Or subtract them off from the total. Okay, the combined gas law. I've also listed some problems to practice for these things as you go. Remember, the combined gas law is a combination of simple gas laws. Charles, Boyle's, Gay-Lussac's. You do not have to memorize those, but you do need to know the combined gas law, which is P1 V1 over T1 equals P2 V2 over T2. So you need to know that law, write it on your note card or memorize it for the final. Here's where people get tripped up with this. One requirement before you use this law is that your temperature has to be in Kelvin. Okay, so people will very frequently, this happened on exam 3, people would plug in a temperature in Celsius. Convert it to Kelvin first. Number 2, make sure, so for example, if you're given 2 different units of volume or 2 different units of pressure, that you have same units on P1 and P2, V1 and V2, T1 and T2, okay? Make sure you have the same units. If you have one pressure given to you in ATM and another in PSI, convert one to the other before you plug those things in, Okay. The next gas law we ran into is called the ideal gas law. It's a little bit different. It's PV, pressure times volume, equals N. This was the number of moles. PV equals NR. This is the gas law constant that we're about to write out, times T, the temperature, in Kelvin. All right, so R, the gas law constant, is a value of 0.0821, and this has a bunch of units. It had units of ATM times liters on top, and then mole times Kelvin on bottom. So you need to make sure that pressure is in ATM and that volume is in liters, and then temperatures in Kelvin before you plug anything in or solve for anything with this equation. Those units are critically important, okay? And make sure you know the R value for the final, okay? Essentially, with the combined gas law and the ideal gas law, it's just algebra. You'll notice that you have 6 variables in the combined gas law. In the combined gas law, or ideal gas law, you have 5 variables. But you always know 1, you always know R. So you'll be given, for the combined gas law, you could be given 5 of the 6 variables and you're finding the 6th. Or you're given 4 of the, 3 of the 4 other values in the ideal gas law that are not R. So you could be given pressure, volume, and number of moles and asked to find temperature. It's just algebra there, but the big thing here where people get tripped up are with the units. So the math is not hard. It's just making sure you set your equation up correctly and that you have things converted to proper units before you plug everything in to solve for your answer. And rearranging the equation to isolate the variable that you're solving for. Okay, so for example, if I was going to solve for temperature, okay, with the ideal gas law, if I was going to solve for temperature, I would want to isolate temperature by itself. And to do that, I would move N and R over to the other side of the equation. So it would look like this, PV over N divided by R. Okay. If I was going to solve for pressure, we'd move volume over to the other side of the equation. So it would be nRT divided by volume. Okay, so make sure you isolate the variable that you're solving for. All right, let's go on to the last 2 things from chapter 8. Heat of fusion and heat of vaporization. So these are 2 terms that you need to know. The heat of fusion is the amount of energy needed to completely essentially completely melt something. So you're transitioning from a solid to a liquid. All right, so once you hit the melting point, however much energy is needed to completely melt something and get it all the way from a solid to a liquid, that's the heat of fusion. Heat of vaporization is the same idea, but the transition from a liquid to a gas. So it's the amount of energy, I'll abbreviate, needed to completely transition from a liquid to a gas. So once you hit the boiling point, you start measuring the amount of energy necessary or that we have to invest to completely boil or vaporize something. It's called the heat of vaporization. Okay. If you want to know more about these terms or just want to refresh yourself, go to the very end of the lecture on chapter 8. One of the very last slides has a great